Okay, so firstly, when you took limits previously, you had certain rules that you applied to take the limit. So one of them was direct substitution. So if you had something like the limit as x approached 2 of some polynomial, you knew that since the polynomial was continuous, you could directly substitute 2 and you'd get an answer. Okay. However, that's not always the case. Sometimes when we take a limit, it's unclear what the answer should be. Okay, those are called indeterminate forms. Okay, so determinant, that we know it has some value. Indeterminate, we don't know exactly what it is. So we may have something of the following form. Something like 0 divided by 0. Okay, in the limit, if you get something with 0 over 0, we don't know what that value is. Okay, also if we get something like infinity over infinity, what kind of value is that? Okay. Next is 0 times infinity, infinity minus infinity, 0 to the 0, and 1 to the infinity. So we see that in all these different cases, it's unclear what the value should be. So for example, infinity minus infinity, how do we get some finite value from that? Okay, so we know infinity, you can take the limit to infinity, but if you're subtracting infinity from that, is it 0, is it 1, 2, you can't really tell. Okay, so these are known as indeterminate forms. Okay, some examples. If we have the limit as x approaches 0 of x over x, we know that should be 1. Okay, so we know that we can divide them and we get 1. But if we just look at the top, that's x. If we look at the bottom, that's x. So separately, both of them go to 0. But if we divide them like this, we know the answer should be 1. Okay, so it has the indeterminate form of 0 over 0, but we know how to get the value. Okay, so the value should be 1. Okay, so that's just one example. Another example is if we have the limit as x goes to 0 of sine x over x. Again, if we take x going to 0, the top part goes to 0, the bottom part also goes to 0, so what kind of value is that going to be? We'll see later in the lecture that this value is actually 1. Okay, but you need to prove that it's 1. Okay, you can't just guess what the value will be. Okay, and then last example, just to motivate this, limit as x goes to 49 of x minus 49 over root x minus 7. So we see that if we substitute 49 at the top, we get 0. If we substitute 49 at the bottom, we also get 0 because it will be 7 minus 7. So again, we get 0 over 0. That should have some value. From these previous examples here, you might think it should be 1, but we'll see that this actually has the value of 14. Okay, so exactly. So even though it has that same form of 0 over 0, from this example you can see that, right, you can't just guess the value 1 based on something at the top, something at the bottom cancelling. Okay, you need to do more work. Okay, so let's put a star here. We see that it's not always going to be 1, even though the top and the bottom have the same limiting value. Okay, so how do we find these values? We're going to find them using L'Hopital's rule. Okay, so this is a rule that we can use to evaluate these indeterminate forms. And again, if your limit has this sort of behavior. So we have something like 0 over 0, infinity over infinity. In particular, these ones, we're going to be using L'Hopital's rule. If we have something of these other forms, 0 times infinity, infinity minus infinity, 0 to the 0, or 1 to the infinity, we need to do some manipulation to get it into those first two forms, one of those two. Okay. You'll see that sometimes it's easier getting it into the form 0 over 0. Sometimes it's easier to work with it in the form infinity over infinity. Okay, that's up to you to decide. Okay, so you have to do quite a few examples, and you'll see which one is best for that example. Okay, and then if you have anything else, you need to get it to that form. Okay, so L'Hopital's rule can be used for anything of the form 0 over 0 or infinity over infinity, like I said. How do we apply L'Hopital's rule? It's very simple. We have the limit as x approaches c, some value, so it could be going to 0, could be going to 1. That just depends on the question. F of x over g of x. This is equal to, by L'Hopital's rule, we have this equivalence. Limit x approaches c, f prime of x over g prime of x. Okay, so again, we can use L'Hopital's rule when we have either 0 over 0 or infinity over infinity. Okay, so there's some other conditions that need to be applied, but we'll see that later when we get to the more complicated examples. Okay, for now, we're just going to be working with this, okay, to avoid any confusion. Okay, and then just a note. So while we're going through the examples, please look out for this. This rule does not apply to infinity over 0, 1 over 0, etc. Things like that. Okay. If you have something like this, the rule does not apply. So you either have to use a different method to evaluate the limit, or you need to do some manipulation first. Okay, but as it states there, if you have something like that, you cannot apply the rule. Okay, if you do try to apply the rule for some of these cases, all of it's wrong. Okay, so please make sure you look out for those cases there. Okay, so if we do have something like that, remember we need to convert it into that type of 0 over 0 or infinity over infinity. So we need to know, how do we convert from some other form to the form of 0 over 0 or infinity over infinity, where L'Hopital's rule applies. Okay. So there's a table that I'm going to go through. Okay, that's going to go through how we convert from one form to the form we need. Please do not memorize this table. The table just shows you how you should proceed with the question. So if you see that the question looks like one of the forms in the table, you should have an idea of where to start. Don't just memorize the table and apply it. Okay, rather look at the table and see, how do I get to this point? Okay, given whatever question you have. Okay, and we'll go through examples to show how we use this table. Okay, so in the first case, if we have 0 over 0, okay, now it's already in the form 0 over 0, but maybe you want to convert it into the form infinity over infinity. Okay, that could be easier to work with. And we'll see now why one is easier than the other. Okay, so this is if we have something like the limit of f of x over g of x, where the top and the bottom have limiting values 0. Now, in the table here, we're going to have 0 over 0 for the first part, infinity over infinity for the second part. Okay, this is already in the form 0 over 0, so we don't need to worry about that. Infinity over infinity, how do we convert that? Well, we know that the top part goes to 0 and the bottom part also goes to 0. But what happens if we have something like 1 over x as x goes to 0? If x goes to 0, then 1 over x goes to infinity. So what we can do is rearrange this a bit so that since we know the top part goes to 0, if we take 1 over that, it goes to infinity, which is what we want. Okay, so we're going to swap this around a bit and instead write it as 1 over g of x over 1 over f of x. Okay, if you simplify that, we get back to f of x over g of x, but now we see that on the right there, if g goes to 0, the top part goes to infinity, as we want, and in the bottom there, if f goes to 0, the bottom part also goes to infinity. Okay, is anyone confused about how you get from that right-hand side term to the left-hand side? Okay, so take this and multiply the top and the bottom by f of x times g of x. So at the top we times by that, at the bottom we times by the same thing. Okay, so that is just multiplying by 1, right? Same thing at the top, same thing at the bottom. But look at the top, we have 1 over g of x times f of x times g of x. The 1 over g of x cancels with the g of x, and the top is just left with f. In the bottom, we have 1 over f of x times f of x times g of x. The 1 over f and the f, they cancel, and we're just left with g, which is what we started with. Okay, anybody still confused with that? Okay, please put your hand up if you're confused. I can go through it again. Okay, let's have a look at the other forms. Okay, so that's the 0 over 0 case. We can look at the infinity over infinity case. So again, it looks something like f of x over g of x, but now the top part goes to infinity and the bottom part goes to infinity. So we can ignore the second one, it already looks like that. We're going to do a very similar thing. If we have 1 over x and x goes to infinity, then 1 over x goes to 0. Yeah, so we want this top part to go to 0 when f goes to infinity. We want the bottom part to go to 0 when g goes to infinity. Okay, so how do we do that? Very similar to what we had before. We can write this as the limit of 1 over g of x and 1 over f of x. Okay, very similar to what we had before. Now, if g goes to infinity, the top part goes to 0, which is what we wanted. In the bottom, if f goes to infinity, 1 over f goes to 0, again, as we wanted. Okay, so it's little algebraic manipulations like this that you should be comfortable with. Okay, if you're not comfortable with working with fractions like this, please revise your work. We're going to be using this a lot. Okay. Let's have a look at the other cases. So if we have something like 0 times infinity, okay, so this is something like the limit f of x times g of x, but here f of x is going to 0 and g of x is going to infinity. Okay, so you need to look at the terms individually to see what's happening with them. What we want to do is convert this into a form where we have 0 at the top, 0 at the bottom. How do we do that? Okay, same trick as before. We know that g is going to infinity, so 1 over g is going to 0. So we can write this as the limit f of x over 1 over g of x. Okay, is anybody confused with that? Okay. If you ask me questions, I can help you. If you stay quiet, I can't help you. Okay, you're here to learn, so please ask questions if you need help. Is anybody confused with this? Okay. Now, if we want to write this in the form infinity over infinity, we're going to do a similar thing again. But now we know f goes to 0. Okay. How do we get it to go to infinity? We need to take 1 over f. So this will be the limit. G can stay at the top, but we need 1 over f in the bottom. Because when f goes to 0, 1 over f goes to infinity, which is what we wanted. Okay, next, infinity minus infinity. Okay, so this one's a bit more complicated, so I'm going to spend a bit more time on this. What we need to do is turn this difference into a quotient. So we've got something like a minus b, we need to turn it into something like a divided by b. Okay, so how do we turn a difference into a quotient? We're going to use an exponential, because we know that e to the power of x minus y is the same thing as e to the x divided by e to the y. Okay, is everyone comfortable with that? Okay, so we've got the limit f of x minus g of x. Let's call that L. We need to figure out what that is. Now this limit is written as a difference. We want it instead as a quotient. Now we know e to the x minus y is the same thing as e to the x divided by e to the y. So let's take the exponential on both sides. So e to the limit f of x minus g of x is equal to e to the L. Okay. Okay, we can take the function on both sides. Nothing wrong with that. Now, we know that the exponential function is continuous. Okay, you would have done that last semester. So if something is continuous, if we have a limit involved, we can take the limit inside the function. We can take the limit outside the function. So here we've got the limit inside the function, but we know that the exponential is continuous, so we can take it outside the function. Okay, if you don't remember your limit laws with regards to continuity, please go over that. Okay, so that's just using our limit laws with continuity. Now, e to the f of x minus g of x, we can separate that out. We have the limit e to the f of x times e to the minus g of x. Okay, now if I have a negative in the exponent, that means I can put it downstairs in the denominator. So I can write this as the limit e to the f of x over e to the g of x, and that is equal to e to the L. Okay, but I don't want e to the L, I want the original limit value, L. So I can take the natural log on both sides. So the natural log, limit e to the f of x over e to the g of x is equal to L. Now we see that limits inside is exactly what we want. We can use L'Hopital's rule on that. So the original one here, if f goes to infinity and g goes to infinity, then e to the f will also go to infinity, and e to the g will also go to infinity. So we've got type infinity over infinity, which means we can use L'Hopital's rule. Okay, so whenever we have something where we have infinity minus infinity, we can use this line of working here, so this procedure, to convert it into a form that we can work with. Okay, so just as an example, if we have the limit as x goes to infinity, e to the x minus x, for example, something like that. So you see we have a difference there. E to the x, that goes to infinity. X also goes to infinity, So we can't do infinity minus infinity. We need to use this L'Hopital's rule, but it's in the wrong form. This is in the form infinity minus infinity. We can't work with that, but we can work with the form infinity over infinity. Okay, so that's going to be for homework. Convert this into type infinity over infinity. Okay, so you have every single step that you need. Here, please settle down. Okay, so you have all the steps that you need. So here I used f of x and g of x. Repeat the exact same procedure, but now with these two functions here. So you have every single step, just replace what you need. Okay, but then that should be some good practice to help you with these. Okay, please no talking. Okay. Okay, so let's have a look at some examples. Okay, please no talking. Okay, like I said in the previous lecture, if you're talking and I make a mistake, you copy down the mistake. Okay. So we have the limits as x approaches 0. Okay, limits as x approaches 0, e to the x minus 1 over x squared plus x. Okay, so what do we have here? We need to look at the top and the bottom separately to see what kind of indeterminate form we have. It might not be an indeterminate form, okay, but we need to check. So in the top, when x goes to 0, e to the x will go to 1. We have 1 minus 1, so the top becomes 0. That's a good start. In the bottom, x squared plus x. It's a polynomial, so we don't have to do any limiting there. Just look at it when x is 0. We get 0 plus 0, that's 0. So the top is 0, the bottom is 0 in the limit. So we have the form 0 over 0. Okay, since we've got it in that form, we can then use L'Hopital's rule to simplify. So this becomes the limit as x goes to 0. Derivative of the top, that's just e to the x. Derivative of the bottom, that's going to be 2x plus 1. Now we check again. Can we do the limit? If we can do the limit using your limit laws that you learned previously, then just do that. If you can't, again, we look for L'Hopital's rule. Okay, so as x goes to 0, e to the x will go to 1. In the bottom, as x goes to 0, the bottom part goes to 1. We have 1 over 1. That's not indeterminate, that's just 1. So we get that that is the value. So here in the last line, we know we did our limit laws. So we just did direct substitution in the top, direct substitution in the bottom, and we got our value. Okay, so like I said at the beginning, you need to know your previous limit laws as well as this new one. Okay, you can't just know your previous one, you can't just learn this one and forget that. You need to be familiar with both. Okay, let's have a look at another example. We have the limit as x goes to 0, 2 sine x minus sine 2x over x sine x. Okay, first thing we check for indeterminate form, which type is it, do we need to convert it to anything else, and so on. So if we substitute 0 at the top, we get 0 minus 0, that's just 0. In the bottom, that's 0 times 0. So we have 0 at the top, 0 at the bottom. It's one of these indeterminate forms. Since it's an indeterminate form, we know we can use L'Hopital's rule. So let's differentiate the top and bottom and then see if it's any better. So this is equal to the limit x goes to 0. Differentiating the top, we get 2 cos x minus 2 cos 2x. And in the bottom, we're going to get sin x plus x cos x. Okay, now we substitute again and see if we still have an indeterminate form. If we get a finite value from this, then that's our limit value. If we get an indeterminate form again, we repeat L'Hopital's rule. So let's see. In the top, if we substitute 0, we're going to get 2 minus 2, that's going to be 0. In the bottom, we're going to get 0 plus 0. So again, we have to use L'Hopital's rule. And we see that it's still in the form 0 over 0. So we write that down on the side, just to tell us we need to do it again. Okay, so again, L'Hopital's rule says that this is equal to the limit where we differentiate the top and the bottom. So the derivative of cos, that's going to be minus sine. We're going to get plus 4 sine 4x. Okay, and then we're going to get cos x plus cos x minus x sine x. Okay, so that is if we differentiate the top and the bottom. Okay, what happens if we substitute 0 now? In the top, we're going to get 0 plus 0, that's still 0. In the bottom, we're going to get 2 minus 0, so that's 2. Okay, 0 divided by 2, that's 0. That's not an indeterminate form, that's just going to be 0. Okay. Any questions on this one? Yeah. Sorry, please keep quiet so I can hear. Yeah? Sure. X cos x. We have a product of two functions, so we use the product rule. So we differentiate the first one, leave the second alone, so we get 1 times cos x. Then we leave the first one, differentiate the second, so we get minus sine x, so we get cos x. With that 1 there, if you want to put the 1, that's fine, and then minus x sine x. So we just did the product rule there. Okay. Any other questions? Okay. Next one. So we have the limit as x goes to infinity of x squared e to the x, e to the minus x. Okay, please settle down. Okay. Yes.
How can you get 4 sine 4x?
4 sine 4x. Oh, sorry, that's a 2. So that's a 2 there. Yeah, so the 2 comes out to the front to make it a 4, but then that still stays a 2. Okay. Just write your name down at the end, and then you can get some points for that. Okay. Okay, no, we don't. There's no talking needed. Okay, everyone knows how the point system works. It's not a surprise. Okay, so we have the limit as x goes to infinity. We've got x squared times e to the minus x. X squared, if x goes to infinity, that's going to be infinity. E to the minus x, as x goes to infinity, that becomes 0. So we've got the form infinity times 0. Now we don't want that, so we can't use L'Hopital's rule. So we need to change this to become either 0 over 0 or infinity over infinity. Now we don't need to do what we did previously. So all of this, you could use the table. But what we could do is just take that e to the minus x. Notice that we've got a negative in the exponent, which means we can move it down to the denominator. So that will be the limit as x goes to infinity, x squared over e to the x. Okay, so there's no real tricks with that. It's just a little bit of manipulation to get it to what we need. Okay, now again, we check for indeterminate form. X squared, that's still going to go to infinity, so the top is infinity. The bottom part, e to the x, that also goes to infinity. So we have the form infinity over infinity. We can use L'Hopital's rule. So we differentiate the top and the bottom. We get the limits as x goes to infinity, 2x over e to the x. Okay, so I'm not going to go through the whole explanation again, but we get infinity over infinity once again. We can use L'Hopital's rule again. Okay, so sometimes you have to do it twice, sometimes you have to do it 3 times. It depends on what you've got. Okay, so once again, that's the limit as x goes to infinity, 2 over e to the x. Now this is no longer an indeterminate form. Okay, so as the bottom, as the denominator goes to infinity, we've got something like 1 over infinity. We know that that tends to 0. So the limit here will be 0. Okay. Anyone confused with that? If you're confused, please put your hand up so I can see. Okay, we've got someone there, thank you. So I'll just do this in pink on the side here. Okay, it's not working. Anyway, on the side here, 2 over e to the x. We can write that as 2 e to the minus x. Okay, maybe that's a bit better to work with. So to find the limit, we can just draw a quick graph to see what happens. So whenever we have e to the minus x, we know that we've got some decreasing function like this. Okay, if it's e to the x, we know that it goes the other way, it's increasing. If it's e to the minus x, we know that it's decreasing. So it's decreasing all the way down. So as x goes to infinity, we see that this function decreases down to 0. So in the limit, we get 0. Does that answer your question? Okay. Anyone else confused with that still? Okay. If you do need to put a sketch on the side to see what the limiting behavior is, please do that. Okay, so remember, you get part marks for your side working. If you do a little graph to show me you understand where the limit goes, I can give you some part marks for that. Okay, so even if you don't know how to do any of this, if you draw the graph and show that it's decreasing to 0, that shows me you understand what a limit is. Okay. Okay, so if you can show me any understanding, you can get some marks for that. Okay, last one. We have the limit as x goes to 0 of x, natural log of x. Okay, again, we've got a product. We look at them separately to see what the limiting behavior is. For the first one, we have just x. As x goes to 0, or x goes to 0, so nothing surprising there. For the second one, the natural log, as x goes to 0, we know that the natural log goes to negative infinity. So again, we have the type 0 times infinity. Okay, so you can have infinity being positive, infinity being negative. It has the same behavior, right? It's going off to infinity. Okay, so what we need to do is rewrite this in the form 0 over 0 or infinity over infinity. Now, since the natural log is already going to infinity, let's leave it like that. Let's change the other term. So we want something like infinity over infinity, right? Because we're going to leave the natural log alone. You could write it in the other form. Okay, I'll put that for homework. But for here, we're just going to stick with this one. So if x goes to 0, we need something that will go to infinity. So if x goes to 0, what can we do? The simplest thing is 1 over x. If x goes to 0, 1 over x goes to infinity, which is what we need. So let's use that. So this will be the limit as x goes to 0 natural log of x divided by 1 over x. Because dividing by 1 over x is the same thing as multiplying by x. Like if you divide by half, that's the same thing as timesing by 2. Right, we haven't changed anything here. But if we look at this indeterminate form, the top part, that goes to negative infinity. Okay. The bottom part also goes to infinity. So we've got this form infinity over infinity. Okay, so we can use L'Hopital's rule with this. Okay, again, that's something like infinity over infinity. Right, I'm not including positive or negative. Infinity is infinity. You can deal with the positive and negatives, for each question you get. Okay, so by L'Hopital's rule, this is the limit as x goes to 0, 1 over x, and minus 1 over x squared. Okay, so that's differentiating the top and differentiating the bottom. Okay. So remember previously when we did derivatives of inverses, we looked at the derivative of the natural log. Okay, so this is something that you need to remember. The derivative of the natural log, that's 1 over x. Okay, so now for these types of problems, you don't need to prove that. You can just remember the derivative of the natural log is 1 over x. However, if I ask you to prove that it's 1 over x, then you need to go through that whole process with the derivative of inverses. Okay, so it depends on where you are in the test. Okay, so what do we get here? We get the limit as x goes to 0. This minus 1 over x squared, we can take that to the top. So we get minus x squared over x. Okay, now please don't treat this as an indeterminate form. It is 0 over 0, okay, but we can simplify. You could use L'Hopital's rule, but that's a bit too much. Right, if you can simplify, rather do that. Okay, so here you could use L'Hopital's rule, but we know we can simplify this. So we get minus the limit x approaches 0 of x, but that's just 0. Okay, so again, you could use L'Hopital's rule for that, but that's unnecessary. We could just simplify. Okay, so this is doing it with type infinity over infinity. For homework, please do this as type 0 over 0. Okay, so a little bit different manipulation. So here we change the x to the 1 over x to get it into the form infinity over infinity. You'll have to do something else for this 0 over 0. And then compare your results. So which method was easier to compute? The infinity over infinity way or the 0 over 0 way? You should get the same answer, but one of the methods will be a bit more complicated. Okay, so that will give you some idea of which way to go given a question. So with some extra practice, you'll know if you get something like this, if I change it to infinity over infinity, that will be very difficult to do. If I change it to 0 over 0, that would be easier to do. Okay, and that just comes with practice. Okay, any questions so far? Okay, so we've looked at cases of 0 over 0, infinity over infinity, 0 times infinity, and infinity minus infinity. Okay, we've got a few more to go through. Okay, so I'll just add on to the table. We're not going to do examples. We'll save that for next time. But it's just to give you an idea of what to do. Okay, so maybe it will come up in the tutorial. Okay, and you can see what to do. Okay, so 0 over 0. We get that if we have the limit f of x to the power g of x, where both of them go to 0. So this base part of f of x, that goes to 0. That exponential part of g of x, that also goes to 0. We don't want that. We want something 0 over 0 or infinity over infinity. So what can we do? Now, since we've got that exponential bit there, we can use logarithms and exponentials again. So let's call this limit L, and then we do a bit of manipulation, and then we'll see what to do. So L, that's the limit, f of x to the g of x. Now I'm going to take the natural log on both sides. So the natural log of L is the natural log of the limit f of x to the g of x. Again, the natural log is continuous. Okay, so we can take the limit outside of the natural log since it's continuous. Natural log of L is going to be the limit of the natural log of f of x to the g of x. Okay, now since we've got an exponential bit there, we can take it out of the logarithm. So if we had something like the natural log of x squared, we can take the 2 down and it will be 2 times the natural log of x. Right, that's just your log laws. So here we get the natural log of L is equal to the limit g of x times the natural log of f of x. Okay. So now, g of x, remember that limiting value was 0. F, that limiting value was also 0. But we're taking the natural log of that. So the g of x, that goes to 0. But the natural log of the f of x, that goes to minus infinity. So we have something of the form 0 times minus infinity. Okay. Now we did a bit of work on that previously. This will be your last homework exercise. Find L in the form 0 over 0 and infinity over infinity. So for a bit of help on that, look at the previous example where we had x times the natural log of x. Yeah, so that was very similar to this. We had something that goes to 0, something that goes to minus infinity. So look at that example, and then you'll see how to proceed here. Okay, just a note on the homework problems. So for anyone that didn't come to the previous lectures, for these homework problems, you get some points if you're the first student to submit the correct solution. And that goes with all of these homework problems. You can pick which ones to submit, or you can submit all of them and get all of the points. Okay, that's up to you. Okay, and again, the deadline will be until Friday, but remember, first person to submit gets it. So start working now. Okay, any questions on what we did today? Okay, so in the next lecture, we will go through the more difficult example. Yeah. Sorry? Register. No, there's no register. So you're all adults. If you want to come, you can come. If you want to bunk the lectures, you can. But I'm not adjusting any marks. If you fail, you fail. Yeah. Okay, settle down, please. Okay, so, if you don't want to come to lectures, you don't have to. I'm fine with that. But if you fail, you fail, right? I'm not going to do anything about that.